In this video, we're going to focus on calculating the electric field due to a line of charge. Now, there's two types of problems that you need to be familiar with. There's the one where the rod is like infinitely long, and there's the other one which has a finite length. We're going to focus on the second case in this video. We're going to talk about how to derive the equations first, and then afterward we'll work on some examples, some practice problems, and things like that. So let's draw a rod. And at the center of the rod, we're going to calculate the electric field at point P. Now what we need to do is we're going to draw a segment of the rod. And this little segment is going to have a positive charge. Now the whole rod has a net positive charge, and that charge is uniformly distributed among the entire rod, but we're going to focus on this small segment. If the rod has a charge Q, then this segment has a portion of that charge, which we'll call dQ. Now the height of the segment is going to be dy. The distance between the origin and the segment we're going to call y. That's this distance right here. And the distance between the center and point P is x. Now we're going to draw a line between the segment of charge and point P. Now if we continue to draw the line, that is going to be the electric field vector, which points away from the charge. Let's call that E. Now this electric field vector has an x component and it has a y component. The x component, we'll call it EX, and the y component is EY. Now let's say if we drew another positive charge, but in this region. If we draw the electric field vector between that charge and point P, it's going to produce an electric field that is directed north of east. And that electric field also has an x component, which, let me put that in a different color. And it also has a y component, which we can call EY. Notice that this electric field and this one are opposite to each other, so they cancel. But notice that these two vectors are parallel to each other, so they add up. Therefore, the net electric field in the y direction, due to the symmetry of this rod, is 0. So we don't have to worry about EY. The net electric field at point P is equal to EX. If we could find EX, then we can calculate the net electric field at point P. R represents the distance between this small segment of charge and point P. So based on the Pythagorean theorem, we know that a squared plus b squared equals c squared. R squared is equal to x squared plus y squared. Therefore, R is equal to the square root of x squared plus y squared. Now let's focus on the linear charge density. The linear charge density, represented by this lambda symbol, is basically the total charge divided by the total length, where L is the entire length of the rod. Now, the length of the rod, we're going to describe it in terms of A and negative A. So relative to this origin, from this point to the top of the rod, that's going to be positive A. And from that point to the bottom of the rod, negative A. So therefore, the length in this situation is represented by 2A. So lambda is Q over 2A. Now, if lambda, which has the units coulombs per meter, represents the total charge divided by the total length, we can also describe lambda for this segment of charge. It's going to be the charge of that segment, dq, divided by the length of that segment, which was defined as dy. Now I'm going to erase the board, but Feel free to draw this picture if you haven't done so already, so you can always refer back to it. So if lambda is equal to dq over dy, then solving for dq, it's going to be lambda times dy. You can get that equation if you multiply both sides by dy, so that these two cancel. Now we also said that lambda is equal to q over 2a. So let's replace this lambda with q over 2a. So dq is q divided by 2a times dy. Now the electric field of any point charge is equal to kq over r squared. So the electric field of the segment of charge that we had on top in the last picture, we could say that dE represents the electric field produced by that small segment of charge, is equal to k times the charge, which is dq, that's the charge of the small segment, divided by r squared. So now that we have that, what's our next step? So notice that we have the expression for dq. dq is equal to q over 2a times dy. So what we're going to do is replace dq with that expression. So dE is going to equal k times q times dy divided by 2a r squared. So let's move this to the top. Now the electric field in the x direction is equal to dE times cosine theta. And if we redraw the triangle that we had before, we know that this is x, here's point P, here's the center, and this represents y, and this is r. Theta is this angle right there. So cosine theta is equal to the adjacent side divided by the hypotenuse. So that's x divided by r. So we have dE, which is k q dy over 2a r squared. dE is basically this equation right here, times cosine theta, which is x divided by r. So what do you think we should do now? What's our next step here? Once we have this equation, we want to integrate both sides so we can get ex. The integral of dE sub x is e sub x. Now let's move all the constants to the front. Notice that dy tells us that everything is a constant except the y variables. So right now we have k q over 2a. I'm going to keep x with the integration symbol. Integral x dy over r cubed. Now our differential is dy, so therefore we need to integrate the function in the y direction. So y is associated with the height of the rod. So we want to integrate it from the bottom of the rod to the top, which is defined as negative a to a. Keep in mind the center of the rod has a y value of 0. So therefore, we need to put negative a and a in our integral symbol. Now keep in mind r, we defined it as being the square root of x squared plus y squared. So we're going to have to use that here. So e sub x is equal to k q over 2a, integral from negative a to a, x dy divided by the square root of x squared plus y squared is the same as x squared plus y squared raised to the 1/2. So if that's equal to r, then r to the third is going to be x squared plus y squared to the 3/2. You got to multiply 1/2 by 3, and you get 3/2. So this is x squared plus y squared raised to the 3/2 due to this 3. Now how can we integrate this function? Now since we have the differential dy, y is the variable, and we're going to treat x as a constant. But we're going to need this x in order to do the integration. So let's go ahead and do that. By the way, just in case you were wondering why we can make x, why we can treat it as a constant, as we integrate from -a to a, this integration is only associated with the y direction, or the y values. The distance between the rod and point P is constant. So as we integrate from -a to a, x does not change. So that's another reason why you could treat it as a constant in this example. But let's focus on the integral of this expression. Let's ignore a -a and a for now. We can add it later. But let's focus on finding the antiderivative of this expression, because that requires some work. So how can we integrate this function? The best way to do this is to use trigonometric substitution. So the first thing that we need to do is take out an x squared inside the parentheses. We're going to factor it out. So this is going to be x dy times x squared. Now if we factor out x squared to get what's inside, divide. X squared divided by x squared is equal to 1. Y squared divided by x squared is what it is. Y squared over x squared. As you can see, if you distribute the x squared to these two terms, you're going to get x squared plus y squared again. Now on the outside of the brackets, not the parentheses, we still have the exponent 3/2. So now let's use trigonometric substitution. Y, we're going to make it equal to x tangent theta. So therefore y squared is x squared tangent squared theta. So now what is dy? If we differentiate this expression, dy is going to be x times the derivative of tangent, which is secant squared, theta d theta. So in this case, x is still a constant, so we don't have to use the product rule. But theta is the variable, so that's where we have the d theta symbol. So now once we have this, we can do some substitution here. Let's replace dy with what we have here. That is x secant squared theta d theta. Now our next step is to replace y squared. Let's replace it with x squared tangent squared theta. So we're going to have x squared tan squared divided by this x squared. And this is all raised to the 3/2. So let's keep that in mind. As always, I'm always running out of space, which is a problem. Let's move this over here. So now what we have is an x squared on top times secant squared. We can cancel these two x squareds. On the bottom we have x squared times 1 plus tangent squared theta, and this is all raised to the 3/2. Now 1 plus tan squared is secant squared. So let's go ahead and replace that. That's a trigonometric identity. You can look it up on the internet. Now we're going to raise x squared to the 3/2 and secant squared to the 3/2. So x squared raised to the 3/2, the 2's will cancel, and this is going to turn into x cubed. So what we now have is the integral of x squared secant squared on top divided by x cubed. And once we multiply these two, we're going to get secant cubed as well. So now let's cancel a few things. We can cancel two x variables, leaving one on the bottom, and two secant values. So we're going to have a d theta on top and x secant theta on the bottom. Now x is a constant, so let's move it to the front. So this is going to be x, and then 1 over secant theta d theta. Secant theta is 1 divided by cosine. So 1 over secant is cosine. So we have cosine theta d theta. So what is the antiderivative of cosine? The antiderivative of cosine is sine. Now don't forget, we need to evaluate it from negative a to b, but not yet. Now if we draw the triangle that we had before, this was theta, here we said this is x, this is y, and this is r, which looks like the unit circle, or the triangle that's related to the unit circle. Now from this equation, or this triangle, you can see that tangent is equal to the opposite side, which is associated with y, divided by the adjacent side. So tangent is y over x, which is similar to this equation. If you multiply both sides by x, you can see that x tangent theta is equal to y. So we can find sine theta from that same triangle using SOHCAHTOA. So sine theta is equal to the opposite side, which is y, divided by the hypotenuse, r. So x sine theta is x times y over r. Now we can replace r with what it's equal to in terms of x and y. We said r is the square root of x squared plus y squared. So this is the integral. Actually, there's one mistake that I need to correct. The x was on the bottom, so this is 1 over x. I almost missed that. So let's fix that. So I'm going to keep the y on top, but the x should be on the bottom. Just want to make that clarification. That's a very, very important step. Now that we have the integral of the function, let's integrate it from negative a to a. So what can we do at this point? How do we evaluate it from negative a to a? Now keep in mind, y is the variable, not x. X is a constant. So we need to replace y with a. So let's plug in the top part first. So it's going to be a divided by x times the square root of x squared plus a squared. And then minus, now we can plug in this one, negative a over the same thing, x square root x squared plus a squared. A minus negative a is basically a plus a, which is 2a. We can add the numerators because they have the same denominator. Now keep in mind that this expression is equal to the integral from negative a to a of x dy divided by x squared plus y squared raised to the 3 over 2. So that's what this is equal to. It's equal to the value of this integral. Now let's go back to our original expression. We said that ex is equal to kq divided by 2a times the integral from negative a to a x dy over x squared plus y squared raised to the 3 over 2. So we have the value of this integral, which is this. We just got to multiply it by k over 2a. So this is equal to k q divided by 2a times 2a divided by x square root x squared plus a squared. So we can cancel 2a. Therefore, E sub x, the electric field in the x direction, is equal to k q divided by x times the square root of x squared plus a squared. And keep in mind that lambda is q divided by 2a, which means that q is 2a times lambda. So if you want to, you can write this equation in terms of lambda. So E sub x is also 2k times a times lambda divided by x square root x squared plus a squared. But we're going to use this equation more often, so just keep that in mind. Now what about EY? We said it's equal to 0 based on the symmetry and the shape of the rod. But how can we prove it? How can we calculate it and show that it's equal to 0? Let's go ahead and do that. So we know that DEY is equal to negative DE sine theta. So relative to this segment of charge, when we drew a vector at point P, EY was in a negative y direction. EX was in a positive x direction. And here's E. So because EY is in a negative y direction relative to this chosen segment of charge, that's why DEY has to have the negative sign. Now based on this triangle, we know this is theta, here's x, this is y, this is r. Sine theta is y divided by r. So therefore, we're going to have negative DE, and we already know the equation from DE. DE is KQ times DY divided by 2AR squared, which we got earlier, times sine theta, which is y over r. So DE sub y is negative KQ times y times dy over 2a r squared. So now let's integrate both sides. So the antiderivative of DEY is simply going to be the electric field in the y direction. And k, q, and 2a are constants that we're going to move to the front. We're going to integrate it from negative a to a, from the bottom part of the rod to the top part. And we have y dy, and this is supposed to be r cubed. R squared times r is r cubed. With long problems like these, it's very easy to make a mistake, so you have to be very careful. Now we know r cubed is x squared plus y squared raised to the 3 over 2, just like last time. So now, how can we integrate this particular expression? We can apply the negative a and a values later, but let's focus on finding the antiderivative of this expression. The only difference between this problem and the last problem is here we have a y instead of an x. Because of that, the integration is going to be a lot easier. Since y is a variable, we can use U-substitution instead of trigonometric substitution. By the way, if you feel that you need to boost your skills in integration techniques, feel free to check out my channel and then look for my calculus playlist. In it, you should find practice problems on U-substitution and trigonometric substitution, so you can master those techniques. Let's make U equal to x squared plus y squared. So what is du in that case? Now keep in mind x is a constant, the derivative of any constant is 0. So the derivative of x squared is 0. It's going to disappear. The derivative of y squared is 2y times dy. And solving for dy is equal to du divided by 2y. So let's replace dy with du over 2y. And let's replace x squared plus y squared with the u variable. So it's u to the 3/2. So notice that the y variables cancel. Let's take this constant and let's move it to the front. So 1/2 antiderivative. Let's move this to the top. So the 3/2 exponent will become negative 3/2. And now we can use the power rule. To do that, add 1 to the exponent. Negative 3/2 plus 1 is the same as negative 3/2 plus 2/2, which is negative 1/2. And then we need to divide by negative 1/2, which is the same as multiplying by the reciprocal of negative 2/1. So we can cancel the 2's. So this is equal to 1 over the square root of u. But there is a negative sign, so let's not forget about that. Now at this point, let's replace u with x squared plus y squared. So this is equal to negative 1 over the square root of x squared plus y squared. So therefore, the integral from negative a to a of y dy square root, or divided by x squared plus y squared to the 3/2, all of that is equal to negative 1 over the square root of x squared plus y squared, evaluated from negative a to a. So x is the constant and y is the variable. We're going to replace y with a. So it's going to be negative 1 over the square root of x squared plus a squared, and then minus negative 1 over the square root of x squared plus negative a squared is just a squared. The negative will disappear. So these two signs will turn into a positive sign. And so we have negative 1 plus 1, which adds up to 0. So the electric field in the y direction, as you can see, is equal to 0. That's how you can prove it. And therefore, the electric field in the z direction is also equal to 0. The only electric field that we have along that center line at point P is in the x direction, which we have the equation for that already. Now, before we work on some practice problems, let's go ahead and review the equations that we'll need. Just the important ones. So here's the rod, and here's the point of interest in which we want to calculate the electric field. And the electric field will be directed in the x direction. So here is our segment of charge that we focused on, and the distance between the segment of charge and the x-axis we've identified as y. R is the hypotenuse, and x is the horizontal distance. So therefore r is equal to the square root of x squared plus y squared. Now L represents the total length of the rod. The bottom part is negative a, the top part is a. So therefore L is equal to 2a. The electric field in the x direction can be calculated using this equation. It's kq divided by x times the square root of x squared plus a squared, where a is simply 1/2 of the length of the rod. So make sure you know this expression and also this equation. In addition, make sure you know that the linear charge density is q divided by L, which is q divided by 2a. So you also need to know this equation. So those are the main equations that you'll need. Now, if for some reason you need to integrate to calculate the electric field, you can use these two equations. If you need to find the electric field in the x direction, start with this expression. It's k times q divided by 2a times the integral from y1 to y2. Now, if you're wondering what those values are, recall that we integrated from negative a to a in the y direction. So therefore, negative a was y1, positive a was y2. So it's going to be the integral from y1 to y2, and then it's times x dy divided by x squared plus y squared raised to the 3 over 2. And now for this expression, we need to use trigonometric substitution. So what you can do is set y equal to x tangent theta. Now you may have to factor out an x squared like we did before, but this is where you want to start. And then you could find the expression for y squared and also calculate dy based on this equation. Now, if you need to calculate EY, let's say if this rod is not symmetrical, there's going to be a y component. So if we calculate the electric field along the center of the rod, there is no y component. The upper part and the lower part will cancel. However, if we want to calculate the electric field that is not in the center, let's say over here, then there will be a y component. So if you need to calculate the y component of the electric field, you can use this equation. So the first part is going to be the same. It's going to be kq divided by 2a, but with a negative sign. Integration y1, y2, and instead of having x dy, it's going to be y dy divided by x squared plus y squared raised to the 3 over 2 power. So that's how you can calculate EY. That's the equation that you need. And just remember, to evaluate this integral, use U-substitution. Set u equal to x squared plus y squared. Treat x as a constant and treat y as the variable. So those are the main equations that you'll need for this particular type of problem. So let's go ahead and work on some examples. So here's a problem. A 1.5 meter long rod has a total charge of 150 nanocoulombs. What is the electric field 60 centimeters east from its center? So here's the rod. We wish to calculate the electric field at point P. And L is the length of the rod. How can we find it? So first, let's make a list of the information that we have. L is 1.5 meters. Q, the total charge, is positive 150 nanocoulombs. X, the distance between the center and a point of interest in which we wish to calculate the electric field directed in the x direction, that's equal to 60 centimeters, which is 0.6 meters, if you divide it by 100. To calculate the electric field in the x direction, we can use the equation kq divided by x times the square root of x squared plus a squared. The only value that we're missing is a. Now a is 1/2 of L, because L is 2a. So this portion right here is equal to a. So a is 1/2 of L, which is 1/2 of 1.5. 1.5 divided by 2 is 0.75. So now let's plug in everything into the equation. K is 9 times 10 to the 9. Q is 150 times 10 to the negative 9. X is 0.6, and then times the square root of x squared plus a squared, which is 0.75. So let's go ahead and do this one step at a time. 9 times 10 to the 9 times 150 times 10 to the negative 9. That's the same as 9 times 150. You can cancel the 10 to the 9 and 10 to the negative 9. So this is going to be 1350 on top. 0.6 squared plus 0.75 squared is 0.9225. If you take the square root of that, you should get 0.960469. The final answer for this problem is 2343. That's rounded to nearest whole number, newtons per coulomb. Now what about part B? Let's calculate the linear charge density. So this part is pretty straightforward. The linear charge density can be calculated by taking Q and dividing it by L, which is the same as Q over 2A. So it's 150 times 10 to the negative 9 divided by 1.5 meters. So it's equal to 1 times 10 to the negative 7 coulombs per meter. And that's it for this problem. Here's another problem that you could try. So we're given the linear charge density, which is positive 45 nanocoulombs per meter. And we have the length of the rod. It's 2.8 meters. And also, we know the value of x, 80 centimeters, which is 0.8 meters. So using this information, let's calculate everything. Let's begin by calculating the total charge contained in the rod. So we know lambda is Q divided by L. So if you multiply both sides by L, the total charge is simply lambda times L. So lambda is 45 nanocoulombs per meter, and if we multiply it by L, which is 2.8 meters, we can see that the unit meters will cancel, giving us the charge in nanocoulombs. So it's 45 times 2.8. So this is equal to positive 126 nanocoulombs. Now that we have Q, we can calculate the electric field. But we need to find A. A is simply half of the length of the rod, which is 1.4 meters. So the electric field in the x direction is K times Q divided by x times the square root of x squared plus a squared. So K is 9 times 10 to the 9. Q is 126 times 10 to the negative 9. X is 0.8. And then times x squared plus a squared. And a is 1.4. So let's go ahead and calculate it. 9 times 10 to the 9 times the other number is equal to 1134 on top. 0.8 squared plus 1.4 squared, that's 2.6, and the square root of 2.6 is about 1.61245. 0.8 times that number is 1.28996 on the bottom. So the final answer is about 879 newtons per coulomb. So this is the electric field produced by the rod along the x-axis, 80 centimeters from the center of the rod. So that is it for this video. You have the equations that you need to calculate the electric field of a long rod of finite length. So look out for my next video on the electric field of a rod of infinite length.